This is Algebra 2, Lesson 7.2. We're doing properties of rational exponents. That's what we're doing. We're using those, and we'll look at them in some real-life problems. Beginning on page 407 in your textbook. We got two definitions to start. The first one is the simplest form of a radical. Remember, when we did the simplest form of squares, it's the same thing. What you need to ask yourself is the same three questions. Is there a perfect factor that makes up the radical? That's the first question. If the answer is yes, you have to simplify it. If the radical is at the bottom of a fraction or in the denominator, you need to simplify it. And if there is a fraction underneath the radical, you need to simplify it. If you get yes for any of those three questions, it's not considered simplified. So just real quick, anytime you see fractions, if you have a radical at the bottom, that's considered not simplified. It doesn't matter what your index is. Again, you typically dealt with square roots in Algebra 1. In here, we're dealing with roots that are other than square, but you can't have this at the bottom. That's what you're looking for. You also can't have a fraction, something like this, underneath a radical. That, again, doesn't matter what your index is. Those two parts are easy, talking about if it's simplest or not. The other one is you need to make sure there's no factor that goes into it. With square roots, it's easy because you know what your perfect squares are. When you have perfect cubes and perfect fourth roots and fifth, and it keeps going on so on like that, it gets a little bit more difficult. What you need to do is you need to make sure that there's no perfect factor that you can simplify or that you can take out. And when we get to problems like that, I'll show you what it looks like. Like radicals are two radical expressions that have the same index and same radicand. What that means is, remember, this number is your index going back to last week. No matter what that is, no matter what that number is, if it were 4, that means it's the fourth root. And it has the exact same thing underneath it, like 3. So the fourth root of 3. This would be a like radical. So if you had something that looked like this, the fourth root of 3, it would be 2 times 4, or the fourth root of 3, plus 3 times the fourth root of 3. These are considered like radicals. Okay, just like 2x plus 3x, you can put that together and get 5x. You can put these two together and get 5 times the fourth root of 3. Same thing. Treat them just like variables. They got to be same expression, same index, or same radicand, same index. This next part's relatively easy. It says let A and B be real numbers, M and N be rational numbers. So numbers that don't repeat in numbers that stop. Okay. The following properties have the same names as those listed in lesson 6.1, but now apply to rational exponents as illustrated. So a to the m times a to the n. Same thing. When you're multiplying the same bases, a and a, just like the bell work, you add the exponents. So you would add 1/2 plus 3 over 2, or plus 3/2, and you get 4/2, which is 2. Okay, so 4/2 is 2, or 3 squared, which gives you 9. So again, same basis, both of them are a. You add the exponents. It doesn't matter that it's a fraction. You add the fractions, just like this, 1 over 2 plus 3 over 2. Remember, when you add fractions, you have to have a like denominator. In this case, they're both 2. So you add 1 and 3 to get 4 over 2, which simplifies to 2. For this one, just like the bell work again, you're raising a power to a power. Same base, a. You do a to the m times n. So 4 to the 3 over 2 squared, you multiply 3 over 2 squared. Again, when you multiply fractions, it'll look like this. 3 over 2 times 2. Remember, you act like as if this is over 1 if you need to see it like that. 3 times 2 is 6 over 2. 6 divided by 2 is 3. That's where that 3 comes from right there. 4 to the third, which means 4 times itself 3 times, 64. Again, all of these rules are exactly the same like it says from lesson 6.1, which we covered already. So this is an easy concept. This is the easy concepts. Okay, so when you have A, B, both being raised to the m, this is one of those instances where you would distribute right here, or you think of this as distributing, because this is not a binomial. Remember, there's two things up there, A and B. But since there's nothing separating them, there's no addition and subtraction separating them, it's one term. It's a monomial. So you distribute the m to both of them, a to the m, b to the m. So 9 times 4, and again, this one's like the bell work too. Remember we did that one where we did it both ways and it come out to be the same. You give the third, or you give the 1/2 power to both of them, 9 to the 1/2 and 4 to the 1/2. So if you need to, you can do it like this. Okay, 9 to the 1/2 times 4 to the 1/2. We even said when we were doing the bell work that we should probably multiply 9 times 4 first. Yes, you should. But in this case, it's showing you how it works. In case you're doing in case you're doing variables which you can't multiply together. 9 to the 1/2 times 4 to the 1/2. Remember what that is, 9 to the 1/2, and this is going back to last week's lesson. This is your index, and the 1 is what you're raising it to. So this looks like this. The 9 is under the radical. The index is the one that goes here, and it's being raised to the first power. So the square root of 9 to the first power is the square root of 9, which is 3. And the other one is to the 1/2 power. 4 to the 1/2 power, it would be like this. 4 would be under the radical. Again, this is your index 2, and it's being raised to the first power. So the square root of 2, or 4, is 2. So 3 times 2 gives you 6. You'll get used to raising things to the 1/2 power of being the same thing as taking the square root of it. The square root is the exact same thing as raising it to the 1/2 power. Anytime you have a negative, same thing. Remember, the negative takes precedent. Ride the elevator first. A to the negative m, rides the elevator, it goes down. 1 over a now becomes to the positive m. So 25 to the negative 1/2 rides the elevator. 1 over 25 to the positive 1/2. And again, we said a second ago, when you raise something to the 1/2 power, it's the same thing as taking the square root of it. So the square root of 25, we know, is 5. So 1 over 5. Then we have the same bases dividing by each other. Both of them say a. A divided by a. That means to subtract the exponents m minus n. So 6 to the 5 over 2 divided by 6 to the 1 over 2. 6 to the 5/2 minus 1/2. Again, if you need to look at it on the side, that's fine. 5 over 2 minus 1 over 2. The bottom number is the same, so your denominator is good. Keep it like that. 5 minus 1 is 4. 4 divided by 2 is where 6 squared comes from. 6 squared, we know, means 6 times itself, which is 36. And then a over b to the 4th power, to the m power, is the same thing as a to the m and b to the m. Again, we think of this like we think of the distributive property as well. So 8 over 27 to the 1/3 means 8 to the 1/3 and 27 to the 1/3. Just like raising something to the 1/2 power is taking the square root of it, raising something to the 1/3 power is taking the cube root of it. Again, if you need to write this in radical form, it would say the cube root of 8 to the first power. The same thing with 27, the cube root of 27 to the first power. Or again, raising something to the 3rd power is the same thing as taking the cube root of it. So 2 over 3. Here's one that we have to do. Example 1. It says use properties of rational exponents to simplify the expression. 7 to the 2/3 times 7 to the 1/3. We are multiplying the same base, 7. Anytime you multiply the same base, you add the exponents. So what we have is 7 to the 2/3 plus 1/2. Now, in this case, you don't have like denominators, so you have to create 2/3 plus 1/2. You have to create them. The least common denominator, the one that these two both go into, is the number 6. So you have to convert them to having a denominator or a bottom number of 6. 3 needs to multiply by 2, so the numerator 2 needs to multiply by it as well. It gives you 4. 2 needs to multiply by 3, so the top numerator needs to multiply by 3 as well, and it gives you 3. So now they're converted to like denominators, and you can add straight across. 4 plus 3 is 7 over 6. So we have 7 to the 2/3 plus 1/2, which means 7 to the 7 over 6. And again, if we were to write that in radical form, you know that this is what goes under the radical. This is the index, and this is what it's raised to after the fact. So you can actually get a decimal equivalent from that by using the calculator. It's unnecessary at this point, though. We'll leave it just like this, 7 to the 7 over 6. The second example for number 1 is 3 to the 1/4 times 5 to the 1/3 cubed. Remember, now we're raising powers to powers. We're not multiplying the same bases. One of them is 3, the other's 5. So both of these terms are going to get multiplied by 3. So 3 to the 1/4 times 3 times 5 to the 1/3 times 3. 1/4 times 3 is 3 over 4, so it's 3 to the 3/4 times 5 to the 1/3 times 3. 1 times 3 is 3, and 3 times 1 would be 3. So that's going to give us 5. So we have 3 to the 1/4 times 3, or 5 to the 1/3. So we have here, we multiply those, 5 to the 1/3 times 3. And this will simplify, everybody. 4 to the 1/3 times 3. We can leave this one as 3 to the 3/4 times 5. And this would actually be its simplified version right here. Not sure why I didn't copy that last line. Oh, there it is right there. 3 to the 3/4 times 5. Okay. C, for example, number 1, C is 10 to the 1/2 divided by 10 to the 1/4. You're dividing the same base as 10. So you subtract 1/2 minus 1/4. 1/2 minus 1/4. When we do this one, just looks just like that. 1/2 minus 1/4 is 10 to the 1/4. If you need to, again, you can do this. 1/2 minus 1/4. You got to convert that bottom number to be like denominators. This one stays the same. This one needs to multiply by 2. So it's 2/4 minus 1/4, which is 1 over 4. And that's where 10 to the 1 over 4 comes from. 10 to the 1 over 4. And the last one from example number 1 is for using properties of exponents. 12 to the 1/6 divided by 3 to the 1/6 to the 4th. Notice that both of these numbers are being raised to the 1/6. So since they're both being raised to the 1/6, we can divide 12 by 3. And we can get 4 to the 1/6 power being raised to the 4th power. 4 to the 1/6 power being raised to the 4th power means you need to now multiply it. 4 times that gives you 4 to the 1 times 4, which is 4 over 6, or 4 to the 2 over 3. Remember, you can reduce 4 over 6 to 2 over 3. Before we get out of here, let's see if we can knock out a couple of example problems. In the margin, everybody, I know there's not a lot of room on the back. Copy down this problem right here. 6 to the 1/2 times 6 to the 1/3. Take about 30 seconds on that one. You're multiplying the same bases, 6 and 6, so you add the exponents. 6 to the 1/2 plus 1/3. Again, remember, anytime you multiply or anytime you add fractions, you got to have the same base. The smallest number these both go into is 6. So 2 has to multiply by 3, so does this one. 3 over 6. 3 has to multiply by 2, so does this one. So you have 3 plus 2, which is 6 to the 5/6 is what that one simplifies to. 6 to the 5 over 6. Try this one. 27 to the 1/3 times 6 to the 1/4 squared. Again, look back at the example. It matches just like number 2 does on the example. Again, anytime you're raising powers to powers, you need to give that second power to both terms. So, or not both terms, but both parts of this monomial. 27 to the 1/3 squared is 1/3 times 2, which is 27. 2 times 1 is 2 over 3, 27 to the 2/3, times 6 to the 1/4 is going to be 6 to the 1/4 times 2. Again, straight across, 6 to the 2 times 1 is 2 over 4. That simplifies to 6 to the 1 over 2. So you have 27 to the 2/3 times 6 to the 1/2. And again, we can rewrite that in radical terms if we had to. And we will finish the rest of this lesson or continue the rest of this lesson tomorrow.